Our last lightning talk is from Haley McPherson on cosmology with the Einstein toolkit. Haley?
Awesome. Thanks so much. I'll just share my screen. Okay, is that working?
Yes.
Awesome, cool. So I just wanted to say a few words, it'll be very, very quick, about the work that we've been doing to do cosmology with the Einstein toolkit. So this is work that I started back at the start of my PhD in 2015 in Melbourne in Australia at Monash University with my supervisors Daniel Price and Paul Lasky. And it's work that I've been continuing here for the last year or so at the University of Cambridge in the CTC. So just a little bit of motivation about why we want to do cosmology. Why do we want to bother using numerical relativity to do something that's so standard, I guess, in Newtonian gravity? So basically the standard model of cosmology, lambda CDM, which some of you might know a bit about, is based on general relativity, but it's under some pretty simplifying assumptions. So these assumptions are that the universe is both homogeneous and isotropic, or the same everywhere and the same in all directions, which, you know, due to the existence of galaxies and humans and planets, we know this is not true. And the current state of the art in cosmological simulations currently use Newtonian gravity to model the nonlinear formation, the formation of nonlinear structures like galaxy clusters and filaments. And so one of the main motivations for this is that the precision of our cosmological surveys is improving to beyond the percent level. So what this means is that even tiny general relativistic effects could become measurable in these surveys as they improve in precision. And so it has long been suggested that both dark energy and dark matter can be partially or even fully explained when you adopt fully nonlinear GR. And this is something that is difficult to actually fully quantify in a framework that uses simplifying assumptions. So to actually really address these questions and see whether this is possible at all, we actually need to remove all these simplifying assumptions. And in addition to that, as these observations that we have are beginning to become more precise, there are quite a few interesting tensions between our cosmological observations and our standard model that are starting to emerge. And it has been suggested that some, if not most of these, can be explained in the context of fully nonlinear GR. So if we use numerical relativity to do cosmological simulations instead of assuming Newtonian gravity, what we can do is actually fully relax all of the assumptions in the standard model and test them. And it also gives us a really useful framework in which we can model general relativistic effects and in our cosmological surveys and make predictions for the kind of things that we might measure. So just a little history of cosmology with the Einstein toolkit. This was first published back in 2016 by Eloisa Bentavegna and Marco Bruni. I'm sure many of you know Eloisa. So this was done using the Cosmo Toolkit thorns, or CT thorns, and it's my understanding that they are available with the Einstein toolkit. And so these provide cosmological initial conditions and evolution thorns for cosmological spacetimes. And specifically for the evolution is something called CT dust. So this evolves just a pressureless dust fluid, so with P equals 0. And so what they've done in these few papers was to just evolve simplified perturbation, so just like a single sine wave perturbation that collapses over time, and studied the rate of this collapse and a couple of other interesting things. So check out those papers for the first cosmology with the Einstein toolkit. But the way that we did it was a little bit different. So what we did is we wrote our own thorn called FLRW solver, which is not yet available with the Einstein toolkit, but hopefully one day. So what all this does is just provides cosmological initial conditions for the space-time and the matter distribution. And then this is just sent in to be used with the regular evolution thorns in the Einstein toolkit. So specifically, we just use GR hydro for our evolution with small pressure. And we use the McLaughlin thorn MLB SSN to evolve the space-time in cosmology. And so specifically take a look at these three papers if you're interested in what we've done. We've done some things like evolving simplified perturbations, mainly for testing purposes. And we've now moved on to more realistic matter distributions like this one here, which I'll show a movie of next, but this really shows the kind of intricate large-scale structure of the universe where you've got clusters of dark matter and filaments and voids. So this actually works pretty well with numerical relativity, which is awesome. So this is just a little movie that we've got of our cosmological box evolving with the Einstein toolkit and our thorn FLRW solver. So you can see the redshift in the top right-hand corner up there. And this box is a gigaparsec on a side with pretty low resolution at the moment. We're only at 256 cubed. But this is really neat because we get a cosmic web that looks a lot like the regular simulations that we have with Newtonian gravity. But simulations like this can tell us about all of the GR effects on our observations due to the inhomogeneous space-time beneath this structure. So this is still a really new field. It only emerged for the first time around when Eloisa published her paper back in 2016. So there's still a lot to be done. And some of the things we're interested in is, well, first of all, it would be great to make this code public so that more people can get interested in cosmology and numerical relativity. And a few things we want to do is we want to look into doing some ray tracing so that what we can do is calculate synthetic observations inside these simulations to make predictions on cosmological observations. So at the moment, this is done separate to the Einstein toolkit in a post-processing code that I've written in the last year or so. Some other things that we're interested in is something which may seem silly at first and did seem silly to me, but was to have a Newtonian solver for the right-hand side of Einstein's equations in the Einstein toolkit. Another reason for this is so that we can make detailed comparisons between the same simulation run with Newtonian gravity and one with full GR. And the problem with this is that I'm sure everyone knows that different codes tend to give different results a lot. So if we could compare the same code with two different gravitational interactions, and that would really help us distinguish the GR effects from just code effects. And another thing we're interested in as well is at the moment, obviously, we're using GR Hydro, which is just on our regular grid with no AMR or anything. But the best way to describe dark matter is to use particle discretization as particles instead of a grid. So that's something that we're looking at implementing in the Einstein toolkit at some point in the future as well. So that's it really. I just wanted to kind of give a little, well, I guess, flash talk into what we're doing, and make sure to check out our papers if you're interested, or send me an email. I have my email back here if you want to ask me anything. But yeah, if anyone has any questions, let me know. Sorry, that might have been a bit quick.
That's okay. We have a question from Nick Hill.
Hi. So my question is that we have second order Lagrangian perturbation theory as well for having same type of simulation. So how does this compare to those simulations? And I mean, yeah, I get it. Like this is this is with the full GR, and those were with some approximations. And so how does this compare with 12PT simulations? And like recently there was, I think as far as I remember last year, there was, that was published in which they used 12PT along with deep learning to get better results for these type of simulations. So I mean, like what kind of a comparison do you think can be made among these two types of simulations?
Yeah, that's a really good question. And as I said, this field is still really young. So there's still loads of comparisons and detailed comparisons that need to be done. But the idea is basically just to test these kind of simplifying assumptions and all of that. So one of the main things I want to say about that is that, I mean, so basically to answer your question, there hasn't been a detailed comparison yet, but this is something that we plan to do in the future. But mainly the reason that we're doing this is because things like perturbation theory, which of course are very useful, but the main assumption is that we're close to some kind of background and some FLRW background. Whereas if you consider fully nonlinear GR, your average space-time does not actually coincide with an FLRW universe. So there are questions surrounding whether the average of our universe actually coincides with an FLRW, which is kind of the base assumption of these perturbation theories. So it is definitely something that needs to be looked into in detail, but we're not quite there yet.
Yeah, okay, thank you.
No worries.
Juan Felipe Bravo.
Yes, hi. Hi, Haley. That was a great presentation. My question is, it is possible with FLRW solver to implement magnetic fields from the cosmological perturbation point of view?
That's a good question. We haven't thought about that yet, but I would say because we're using GR Hydro, there would be a way to put a magnetic field in there. And like the code itself is super simple. All it does is just specifies the cosmological space-time. And so it's definitely something that you could implement at some point, but it's not something we've looked into yet, no.
We have another question from Manas Vishal.
Yeah, hello. I'm okay. So have you heard about Gadget 2 simulations? I have done a simulation from using it. And how does the result compare from it using the large scale structure formulation and the filament formulation?
Sorry, did you say Gadget 2 simulations?
Yeah.
Yeah, sure. So yeah, so again, I haven't looked into comparing directly with these Newtonian simulations as of yet. But there have been some other groups who've done kind of like a preliminary look into the differences between these simulations. But basically, it's tricky to compare them because of gauge differences. So obviously, in full numerical relativity, we're in a different gauge to the Newtonian simulations. So the only way you can do it is by looking at the effects on specific observations. So I'm not sure about Gadget 2 specifically, and maybe I'm going totally off topic, but as far as I'm aware, the only detailed comparison is to do with the lensing power spectrum, and this was by a different group, and they found very small differences between the Newtonian simulations and the full numerical relativity.
Okay, thanks a lot.
No worries.
Abhishek, I think I accidentally lowered your hand for you twice. If that's the case, you can ask your question now.
Yeah, thanks. So could you clarify the statement? Sorry about my mic. Could you clarify the statement that dark matter energy can be explained with gravitational cosmological simulations? Because this, if I'm understanding, is different from what was mentioned in the morning, right, about modifications to general relativity. This is just regular general relativity on a cosmological scale, right?
Yeah, that's right. So this is something that hasn't been looked into in any detail beyond the theoretical. So well, I've done some preliminary investigations into it, and the effect seems to be small. But the basic idea. So now I'm not so sure about the explanation for dark matter, but in terms of the explanation for dark energy, it's basically what I said with the previous question before, is that if you consider the averaged evolution in terms of fully nonlinear GR, it does not coincide with FLRW. So what you end up getting is when you look at the averaged equations in fully nonlinear GR, you end up with the equations that correspond to the evolution assumed in the standard model plus an extra term. And so the basic idea is that this extra term is just the lambda that we add in as dark energy. And so when you consider the fully nonlinear dynamics and averaging over them, that as opposed to assuming that our universe has this particular background cosmology, you end up with an additional term anyway, which can kind of replace dark energy. So this is something that's been debated for like 40 years or something like that. And so it's not a new idea, but the only way that you can actually calculate it is by evolving the fully nonlinear matter distribution and calculating the averages. So there's a lot of subtleties that go with this. So I'll just ask you to check out my latest paper on that one, and you can have more of a read about it. I hope that made sense.
Yep, thank you.
No worries.
And we have another question from Peter Diener.
Yeah, so as far as I could see, your simulations are currently done in Unicred, right?
Yes, that's right.
Do you ever imagine having to do mesh refinement for the space-time evolution?
Yeah, we've thought about it. At the moment, we don't really think it will provide much of an advantage because if you look at like this space-time, you can see that like most of the grid is covered by some kind of structure.
Yeah.
So if we look on smaller scales where we have, say, a really large void, then yeah, it might come in handy. But in terms of these kind of size simulations that we're looking at now, it wouldn't really pose too much of an advantage, we think.
Yeah, that's what I was thinking as well, yeah.
Yeah, sure. Awesome.
Okay. Oh, we have another question. Liu Haiyang.
Yeah, I have a question about, I want to know if the ray tracing you mentioned in your PowerPoint can apply to the black hole. I mean, just like the Einstein Event Horizon Telescope.
Yeah, that's a good question. So at the moment, I'm nearly finished writing it, and I'm trying to keep it as general as possible. So the idea is that you would just input some kind of space-time, and then, you know, where you want your observer to be and where you want your source to be, and then you would So, I mean, in theory, yes, it would work for a black hole, but I don't know much about ray tracing around a black hole. I'm not sure if there's any special considerations to take into account in terms of the horizon or anything like that. So I'm writing it with cosmology in mind, but also trying to keep it as general as possible. So.
Okay, thanks.
No worries.
I have one more question from the chat. It says, I want to know how many CPU hours a simulation like yours takes.
That's a good question. I don't have an exact number in mind, but we ran this on a pretty low number of cores just because we couldn't really figure out the scaling too well, because at the time I was working with myself and my supervisors who are non-Einstein toolkit experts. So it took the simulation took a couple of months, maybe one month or 2 months on of order 30 cores or something like that. So I'm not sure the exact number of hours, but it could be a lot faster.
All right, I think that exhausts our questions. This is the end of the content that we have provided for this workshop.